You have fallen into Event Horizon with John Michael Godier. This episode is sponsored by porkbun.com. Porkbun is a refreshingly different domain registrar that's different from other ones like GoDaddy or Namecheap. They've got the lowest prices on hundreds of different domain extensions, so you can create a website, blog, online portfolio, or anything you want to show off what you do. Everything from the usual .com domains to the unique ones like .pro, .dev, and .xyz. Every domain name at Porkbun comes with tons of freebies like SSL certificates, whois privacy, DNS, and URL forwarding, because why pay for things that should be free, right? They've also got free trials for their link in bio tool that makes it easy to keep links to all your platforms in one place, plus web and email hosting trials. If you like Event Horizon and you love new tech, check out their new AI-generated search tool using ChatGPT that is changing how people search for domain names. All of these wonderful features and tools are backed by an incredible support 365 days a year. The Porkbun website is simple to use and easy to navigate. You can manage everything about your new domain from one place, and they don't do upsells like those other places do, so you're not being pressured to pay for products you'll never use. Click on the link in the description below and use code EventHorizon24 to get $1 off your next desired domain name at Porkbun. John is joined today by Dr. Earl Bellinger. Dr. Earl Bellinger joined Yale University as assistant professor in the Department of Astronomy in January 2024. His research intersects astrophysics and artificial intelligence with a particular focus on stellar evolution, structure, and pulsations. He utilizes seismic data from stars to determine their inner structure and ages, which in turn enables further study of the exoplanets they host, the galaxies that host them, and their own underlying physics. He carried out his PhD research at the Max Planck Institute for Solar System Research and Yale, and he held postdoctoral research fellowships at the Stellar Astrophysics Center in Denmark and at the Max Planck Institute for Astrophysics in Germany.
Dr. Earl Bellinger, welcome to the program.
Thanks for having me.
Now, Doctor, we have these weird ideas of the possibilities of the universe where things might exist that we haven't necessarily seen or observed, but there's no reason that they don't. And one of these is the so-called Thorne-Zeitkow object, where a neutron star can become embedded inside of a red giant. And stellar mergers, neutron star mergers, we see mergers, but there are other types of mergers possible. And in this case, a primordial black hole left over from the very advent of the universe. What exactly, in the early days, created primordial black holes, and why do we think they exist?
Great question. So to start off with, we don't know for sure that primordial black holes exist, and they may not have, but there's natural reasons to believe that they may have been formed in the immediate aftermath of the Big Bang. This idea goes back to Stephen Hawking himself. Although there were actually others a bit less famous who worked on the same idea around the same time. And in fact, an interesting bit of history here is Hawking's greatest contribution, arguably, to science is discovery of Hawking evaporation. You know, the idea that black holes evaporate over time, lose mass due to quantum mechanical effects. And the history that's interesting is how he actually came upon this idea, and that was through his hypothesizing of these primordial black holes. And so the basic idea is that in the very early universe, if you wound back the clock from today, you would find the universe to be a very hot and dense state. And in these conditions, you could have local overdensities of space-time collapse directly into a black hole. And the interesting thing is that these black holes could span the entire gamut of possible masses. Unlike a normal black hole that we think of, normally to create a black hole, you need a massive star to die. Something like, let's say, 10 times the mass of the sun will explode and leave in its wake a black hole, a massive black hole, something at least several times more massive than the sun. But these black holes that are created in the early universe, their mass would be proportional to the age at which they were formed, to the power 3 actually, so time cubed, which means that you would get a wide range of black holes emerging out of the Big Bang, some with extremely low masses, the mass of, let's say, a moon or an asteroid, as well as potentially some supermassive black holes. So right at the beginning of time, you would have this spawning of a potentially enormous number of compact objects.
Are we looking at a contender for explaining dark matter with the primordial black holes?
That's exactly right. Yeah. So there's been an explosion of interest in primordial black holes as a dark matter candidate. I think we're up to a rate of something like 500 publications per year on this topic, and increasing every single year. Most of these papers, they look at various masses of black holes to ask if these could be the dark matter. And there's very good reason to believe that it could be primordial black holes. For one thing, black holes are the only dark matter that we currently know of to exist. I mean, ordinary black holes are basically by definition dark matter, right? So that we know that ordinary black holes, it's funny to call them ordinary, of course. We know that they constitute some of the budget of dark matter. But the ordinary black holes that we look at, the ones that are formed from dying stars, we know that they would have to be a tiny fraction of the dark matter. The dark matter problem is really that the black holes that we know about aren't sufficient to account for all of the dark matter. And it's kind of an extraordinary statement when you step back and think about how many black holes are actually around, that we know pretty well are around. So first of all, we have measurements from LIGO, the interferometer, of black holes merging, right? And these are very new measurements. They're from the last few years. Nobel Prizes have been awarded, and they've discovered about 90 merging black holes. In addition to those, we have the supermassive black hole at the center of our galaxy. Another Nobel Prize was awarded for that. And there's a bunch of galaxies in our universe that we can see very clearly. And we have plenty of evidence that basically every galaxy has a supermassive black hole at its center. So there you have a collection of black holes. And then in addition to those black holes, right? In addition to the 90 that we've observed from gravitational waves and the huge number that we can see from other galaxies, well, you can do the basic accounting of every massive star should die and leave a black hole behind. So how many black holes should there be in our galaxy from that process alone? And that leads to the astonishing fact that most people, I think, have never stopped to appreciate, which is that there should be at least 100 million black holes in our galaxy, in the Milky Way alone. But that's not enough. That's not enough black holes to account for the dark matter that we realize that we need to make our theories work, to explain the observations. And so that's really the dark matter problem, is where's the missing mass? One way that you can get that missing mass is by simply saying, okay, maybe you have some additional black holes not created from the death of a massive star, but created in the immediate aftermath of the Big Bang. And this is a very compelling solution because, for one thing, it doesn't require us to change the known laws of particle physics. Most other candidates say, okay, we have a really good theory of particle physics, but we have this dark matter problem. So let's change our theory of particle physics and say, introduce a new particle. That particle could be dark matter. And then the question is, well, why did you change your theory of particle physics? This is a natural solution because this is just... even if primordial black holes don't account for the remaining dark matter, there's still good reason to believe that probably some exist. Probably the Big Bang made some number of black holes. The question is, did it make enough to explain all of the missing dark matter?
I think the big question is that if you have an enormous number, we were talking numbers like 100 million for the Milky Way, but an enormous number of primordial black holes, that might suggest that there's one relatively close by, right? That we could use as a laboratory.
That's right. Yeah. So the interesting calculation comes out to be that if these, let's say, asteroid-mass primordial black holes are making up all of the dark matter, then you would find that on average, they're separated by a distance of about 1 astronomical unit. So the distance from the Earth to the Sun. And so this is far more densely spaced in our galaxy than stars are. So in between every pair of stars, you would have huge numbers of these primordial black holes. And so probably at any given time, there's one lurking around the solar system. And in fact, there's been a number of studies that have tried to use the solar system itself to test whether or not primordial black holes are lurking. For instance, one of my main collaborators, Matt Kaplan, he uses the moon as a primordial black hole detector, with the idea being that if a primordial black hole smashed through the moon, it would create a crater, but that crater would look different than a normal meteor hitting the moon. And so from lunar craters, he's able to constrain the number of primordial black hole impacts. Additionally, there's things like if a primordial black hole passed through the sun, well, we expect these things to be moving very quickly. And so probably such an object would pass through the sun like a bullet. And it wouldn't really have any long-term effects on the sun if it did that, but it would excite some oscillations in the short term. And so maybe by continuous monitoring, we can see if the sun flares up in an irregular way from a primordial black hole just passing right through it. And lastly, there's a hypothetical planet 9 that could be in our solar system. There's a list of things that people say suggest that we might have an extra planet in our solar system. The most compelling of these being that we have a bunch of long period comets that seem to have somehow correlated orbits. And the way that you can correlate those orbits is by introducing a massive body in the outer solar system. But people have looked at where such an object should be and so far found nothing. And so one possible idea is that this is actually a primordial black hole lurking in our solar system.
Lurking in the solar system. Now, what could we do in physics if we had access to a close by asteroid mass primordial black hole? What could we learn from it?
That's a difficult question. It's hard to make some definitive statements without immediately veering into sci-fi. There was a nice sci-fi novel that people have been, since I started working on this topic, people have been coming out of the woodworks to tell me about fun sci-fi that connects with this. One of them, I can't remember the name, but scientists had either captured or created a tiny black hole here on Earth. And it basically plummeted through the Earth and then oscillated through its core and wreaked havoc. So it's hard to imagine how you could interact with this system without somehow having catastrophic effects. In fact, even really finding and isolating it would be an extremely difficult endeavor. So it's hard to say what we could do. Although I can speculate a little bit. I mean, first of all, if we were somehow able to capture such a thing, then you would be able to study Hawking evaporation up close because such an object would be essentially leaking mass. I don't know how you would contain it without it accreting its container. And that's a very difficult problem. But imagine some futuristic technology. We would probably be able to study Hawking evaporation in a real laboratory setting. And that's actually an extremely exciting possibility because black holes kind of marry quantum mechanics with general relativity. Normally, most things you work on require either one or the other, or actually usually neither. But black holes are one of the few examples where you get the extreme distortion of space-time from general relativity, but you also have this leaking of particles from quantum mechanics. So we would be able to basically study Hawking's theory in detail.
And that in turn would tell us something about the old age of the universe when there's nothing left but evaporating black holes. And if you can go and look at that, then you can sort of extrapolate what's going to happen in the far future of the universe, right?
That's right. And something like 10 to the power 100 years from now, when the universe is dying a heat death, all that will be left after protons decay are these, maybe proton decay is, I'm not sure which of the two is the last event of the universe. But yeah, you have this very long time span of Hawking evaporation. Although even that is, it's very uncertain. I know there's some physicists who are working really in detail about what modern physics has to say about Hawking evaporation. And I can't claim to be an expert on any of that. But I've attended some talks by some people who work on this who say that the picture is not so clear because normally you expect that a black hole evaporates and becomes a black hole of basically just smaller mass. But what the string theorists are evidently telling us about Hawking evaporation is that when a black hole has evaporated half of its mass, it turns into a somewhat different kind of object and its evaporation could slow. And so learning, if we had one up close, we could then try to study this process in detail. And that might tell us a lot more about these unifying theories of gravity, theories of everything. But again, I can't speculate more on that topic.
Now, let's say that, all right, let's say we have them. There are primordial black holes out there that are left over from the beginning of the universe, and they're interacting. They're doing physical things. And one of those is one could end up inside of a star. Tell us about that idea.
That's right. So this is, again, an idea that goes back to Stephen Hawking, which is why I've suggested calling such an object a Hawking star. So in the same paper where Hawking suggested the existence of primordial black holes, he then went on to make a series of, can we call them wild speculations? Hawking was an amazing guy because he was not only one of the most brilliant scientists the world has ever seen, but he also didn't shy away from just like coming out with crazy ideas left and right. And so Hawking suggested a number of ways that these primordial black holes could, let's say, rear their heads. And one of them, he suggested, like, you could look at one of those cloud chambers where you see like electrons flying through and making trails. He said, well, there's always a number of things that are unidentified in those cloud chambers. Maybe those are primordial black holes transiting through them. And another one of these kind of throwaway speculations that he made was, well, maybe such an object could find its way into a star like the sun, and as it consumes the sun from within, it would generate enormous luminosity, and that could be a fuel source for stars. And the reason why he actually was bold enough to conjecture this was because back in the day, we had the very famous solar neutrino problem. Basically, that the fuel source of the sun should be nuclear reactions, but nuclear reactions generate neutrinos. Those neutrinos make their way to the Earth, and we can measure them. But we had only measured about a third as many neutrinos as predicted from nuclear theory. And so Hawking said, well, one way to reduce the neutrino flux would be if the sun had a primordial black hole at its center, supplying the remaining, let's say, 2/3 of the solar luminosity. So you get some from nuclear fusion, accounting for a third of the neutrinos, but you get the rest from accretion onto this compact object. And so, yeah, this was clearly a pretty wild idea, but some people looked into it and started making models of what it would be like if you had evolution around a primordial black hole. The most famous of these was probably Donald Clayton, who's a well-renowned nuclear astrophysicist, wrote an influential textbook. And so he had this great paper about creating partial evolutionary models of stars with black holes at their center with the aim of quantifying whether or not the sun could possibly have a black hole at its center. And he found some maximum mass that black hole could be. Now, of course, in the intervening years, we found out the true solution to the solar neutrino problem. And so interest in this topic died out. So that's where I kind of came in fairly recently. I'm a big fan of history of science, constantly reading old papers just because I find them very enjoyable. And so I found this literature that kind of died out in the 1970s and thought, hey, back in the day, they had this model where they were motivated by the solar neutrino problem, and that kind of stopped this research program dead in its tracks. But we have new motivation for searching for these things because it's become a very popular dark matter candidate. And so me and my collaborators, we kind of revived this scenario, and we started looking at what would happen if stars were born from a cloud of gas and dust that happened to contain a primordial black hole inside of it. Now, we expect this scenario to be rare. If you take estimates of how many primordial black holes we might expect to be in our galaxy, and you take estimates of how many of those might get trapped in star-forming regions, you get something like somewhere between 1,000 and 10,000 stars in our galaxy might be born with a primordial black hole at their center. And so the question is, what happens to those objects? That's something that was never actually addressed in these historical papers because they only really looked at the sun, right? Which I have to admit is a very logical thing to do. You know, it would be a gross oversight for humanity if our sun had a black hole at its center and we just didn't know it. So the first thing we wanted to do was reproduce those works and see if we can put an upper bound on, you know, the maximum mass of a black hole that could currently be in our own sun. But to sway anyone's fears, we don't think that there's probably not one in our sun. But then the question became very interesting. If a star is born about one of these black holes, what would happen to it? Well, here's where things get very difficult and uncertain, I have to say, because we don't understand black hole accretion physics. By we, I refer most specifically to myself, but also more generally to the wider scientific community. There's a lot of outstanding problems related to black hole accretion physics. And so we partnered with several experts on black hole accretion, and we developed several different accretion models for how a primordial black hole would grow inside of a star that was born around it, basically eating it from within. And we presented a few different interesting outcomes. And we consider these to be basically the extreme scenarios. Maybe the truth would lie somewhere in between, or maybe some of these scenarios would be realized depending on what type of star captures the primordial black hole. But the broad outcomes are as follows. In the beginning, so this is true of all the scenarios, In the beginning, if the black hole is very small, it accretes very slowly, actually. It's like this tiny little funnel that you're trying to get matter into. And so the black hole is trying to grow, but even in the dense environment of a star, it grows very slowly. So basically, all models of black hole growth agree with that. If you had a black hole at the center of the sun that was like, let's say, less than a trillionth of the solar mass, then it wouldn't even need the sun over the lifetime of the universe, the present age of the universe. Of course, in the future, eventually it would. But once you get the mass above that, then you start getting into a regime where the growth can become efficient enough to change the fate of the sun. Then you start to ask, okay, what happens as the black hole eats the star? Well, some luminosity flows out from this event. So you get to the question of how much. And this is where we started to develop several different models for the luminosity flowing out from the accreting black hole. And so the first scenario that we looked at is where the outflowing luminosity of the black hole, accreting black hole, is balanced by the infalling gravity. This is the so-called Eddington limit. It's also dictating how massive stars evolve. When you get into this regime, this means that the growth of the black hole is more or less regulated by the surrounding plasma. And here you have this really interesting phenomenon that I think nobody expected. I don't know, I think it's pretty cool, which is that the star becomes entirely powered by the primordial black hole's accretion. It's able to generate such a powerful luminosity that it actually shuts off nuclear fusion in the star. And this is what Hawking had in mind. This is why it was able to reduce the neutrino flux. And so that could be the state of the sun for some time. But then what ends up happening is that you generate such an enormous luminosity that the star puffs up into a giant, which I think nobody really expected. That was the unexpected outcome. And furthermore, the star becomes fully convective. So yeah, energy can be transported in three ways: convection, conduction, or radiation. Normally, the energy through the sun, the innermost 70% of the sun is carried by radiation, and then the outermost 30% is carried by convection. When the sun becomes a giant, its convective envelope will deepen, but not entirely. It'll go close to the core, but the core will still be transporting energy by radiation. But not in the case of these Hawking stars. Then you get a red giant that's transporting all of its energy by convection. And so here's where you get a very unique type of star that's called a red straggler. Now, we have observations of about 500 red straggler stars, but their origin is unknown because normal stellar evolution theory does not predict the existence of red straggler stars. You have to invent other scenarios to get a red straggler. And so Emily Liner has led an interesting series of papers saying different scenarios that could result in red stragglers, such as through binary interactions and magnetic fields. Well, this is a new pathway to red straggler stars, which is accretion onto a black hole at their center. So that's one scenario. And the interesting thing about this scenario, this first scenario of the three, is that it could potentially live as this Hawking star could potentially live as a red straggler star for billions of years. And so if there's 10,000 of these in our galaxy, we would look around and they would be in that state for such a long time that we would actually be able to observe them and study them and potentially determine they have a black hole at their center. Okay, the second scenario is the same as before, but you don't have this balance between the outflowing luminosity and the inflowing gravity. There's no such thing as an Eddington limit in this case. Then you actually get the same sequence, the same evolution into a red straggler star, but it happens much faster. Instead of living as a red straggler for billions of years, it might only live as a red straggler for millions of years or even less. So same scenario. But then the third scenario we looked at is what happens if you have a phenomenon called photon trapping. So for instance, if your star is rotating very, very, very slowly, you might fall into this scenario. And here, you actually don't puff up into a giant anymore. The photons that the black hole accretion generates aren't able to escape and diffuse through the star. They never trigger this convective energy transfer process. Instead, they're just dragged directly into the black hole. And in that case, you would see stars just disappear from the sky. And this is also a very interesting observational consequence of the theory. Now, there are scenarios where we actually expect stars to disappear from the sky. These are so-called failed supernova. So there's a very narrow range of masses of massive stars that when they die, instead of exploding and creating a big supernova, they would have a so-called fail supernova where they more or less collapse directly into a black hole. And so people are looking for those, but that would be a massive star dying. In this case, we might have low mass stars, star mass of the sun, for instance, just disappearing from the sky. And some people have told me that there's observations of these disappearing stars. And so far, there's no real explanation for why such a star could disappear. And so that's another interesting, potentially observable consequence of this scenario.
Straggling stars, and red stragglers aren't the only ones. There's also blue and, as I recall, yellow. And these stars are weird because they sit sort of outside of the normal Hertzsprung-Russell main sequence. These things are just off. And yet we see them. Now we see with blue stragglers, we see them sort of congregating in the centers of star clusters. But with the red stragglers, is that not the case? In other words, are they just evenly distributed and may bolster the idea of them being related to primordial black holes?
Yeah, that's right. So yeah, maybe I'll try to give a description for the non-astronomer to understand what a straggler is. So we can make predictions for how stars should live their lives. The main thing that changes from star to star that dictates how its evolution will go is the mass of the star. So the sun will have a particular evolution, and a star of a different mass will have a different evolution. But another star with the same mass as the sun will basically have the same evolution as the sun. There's some things that could change depending on the chemical composition that the star was born with. But the main thing that changes is the mass. Now, what's very interesting is that there's some collections of stars out there called clusters. These might have 1 million stars in them. And these stars are essentially all born at the same time. And because they're all born from the same cloud of gas and dust, they have the same chemical composition. So if 2 stars in that cluster have the same mass, we really expect them to have essentially the exact same evolutionary path. And so what you can do is you can take theoretical models of stellar evolution. What do I mean by that? Well, simply you take some equations that we think approximate the structure of a star, such as like we assume that the star is spherical, we assume that it's self-gravitating, we assume that it's supported by nuclear fusion. You take these equations, you put them together, put them into a computer, and you solve them. Actually, I'm on a team of people who release popular software called Mesa for doing these calculations. It's open source software, so anyone can download it. Anyone can compute the evolution of stars by themselves. It solves this set of equations that predict how a star will live its life. So in a cluster, you have these 1 million or so stars. They're of the same chemistry and they have the same age. And so the only thing that distinguishes them is their mass. And so you can take these predictions of theoretical stellar evolution and you can ask, okay, this population of stars, the only thing that differs between them is their age. And so you can weave together all these models to ask, okay, what are the luminosities of these stars? Like how bright are these stars? And how hot are these stars? And so this is the so-called Hertzsprung-Russell diagram, simply plotting the luminosity and temperatures of stars. And yeah, the first thing people learn in astronomy usually is that this diagram isn't random. It has a very definite structure. And this is where the term main sequence comes from. Most of the stars are in the first phase of their life, which is burning hydrogen in their core, like our sun. This is the longest lived phase of stellar evolution. And so on the Hertzsprung-Russell diagram, you see a band that we call the main sequence where most of the stars live. And so when you look at this diagram, nearly for a cluster of stars, right, you measure all their temperatures, all their brightnesses, and then you plot that. All of those stars line up basically on this sequence. We call this an isochrone. Iso meaning same and chrone meaning age. So same age. And that's pretty compelling evidence that these stars are born at the exact same time because they line up very beautifully with the theory of stellar evolution for what we predict stars to look like, groups of stars at a certain age. Actually, this is considered some of the most compelling evidence that our theory of stellar evolution is approximately correct, is that we can predict these color magnitude diagrams of clusters of stars. Okay, so almost all of the stars line up on this diagram along one of these so-called isochrones, same age lines. Except there's always some stars that don't. Well, any star that doesn't is referred to as a straggler. And a straggler just because it's straggled away from where the isochrone says all these stars should be. Now, there's a bunch of different ways that you can be a straggler. For example, if you look at a cluster, well, it might be very far away. There might be a star in between you and the cluster. And so when you look at all these stars, you think that star is a part of the cluster, but it's actually not. And so it falls in a random place on your diagram, not along one of these isochrones. And you're like, okay, well, It straggles because it's not actually part of the cluster. Thanks to missions like Gaia, we can actually do cluster membership very reliably now. And so we can kind of get rid of the non-members. Okay, but then you have a bunch of these stars. Some are blue stragglers, some are yellow stragglers, some are red stragglers. The most common, most famous of these are the blue stragglers. These are stars that they straggle to the blue. Well, what does that mean? Well, when we measure the temperature of a star, if it's hotter, it'll be bluer. And so these stars are hotter than the normal main sequence. Now, how do you get a star that's hotter than the normal main sequence? Well, normally, more massive stars are hotter than less massive stars. And what happens if two stars merge together? Well, they form a more massive star. And so this can happen at any time in the lifetime of the cluster. You know, a cluster might have 1 million stars in there. They're all very close together. Note, however, note that our sun is an isolated star, right? Our sun does not belong to a cluster. There's no other stars around us, right? All the other stars are really far from us. If you were in a cluster, there'd be a star right next door. You know, the night sky would be like super, super bright all the time. So if you have this cluster with 1 million stars, you might have a couple of these stars smash into each other and merge. Or maybe some of the stars were just born next to each other in a binary, and binaries naturally often merge. In fact, we know that most massive stars are born in binaries. It's basically the typical state for stars, let's say 10 times more massive than the sun. Pretty much all of them are not born alone. Some of them are even born in triple systems. You know, there's 3 stars instead of 1, or even quadruple systems, or even higher order systems. And so if stars merge, then they'll become more massive. And if they're more massive, they'll be more blue. And so these are the blue stragglers. Well, the red stragglers, it's not so easy. There's not so many formation channels for these red stragglers. And so what do I mean by red? Well, same kind of story. You have this isochrone defining where you expect all these stars to be. And the stars are to the red of this normal part of the diagram. And in particular, the red stragglers are to the red of the red giant branch. So when the sun evolves, so currently it's fusing hydrogen in its core, and it's been doing that for 4.5 billion years. In another 5 or so billion years, it will exhaust its central hydrogen supply, and it will continue its evolution fusing hydrogen in a shell around its core. And there it will puff up into a red giant star and consume the Earth, which is, of course, slightly horrifying. And so when it does that, it becomes a red star, and it becomes a giant star. So this is the red giant branch. Well, stars can be to the red of that red giant branch. So these are lower temperature stars. And this is where the red stragglers are. And like I said earlier, we know of about 500 examples of these red straggler stars. So when you look through data archives of these clusters, you see like 95% of them fall along these isochrones, but you have a few stragglers. And every so often, you see 1 or 2 stars that fall to the red of the red giant branch. So cooler than usual. And yeah, they're very difficult to explain. So this is one formation pathway for a red straggler star, which is that they have a black hole at their center.
The idea of the sun evolving and becoming a red giant and swelling and swallowing up the Earth, could that equation be changed by the presence of a primordial black hole in the center of the sun, meaning that might the sun's red giant phase be changed and Earth gets spared just because it has a primordial black hole?
Yeah, that's exactly right. So yeah, the fate of the sun is rather dramatically different if it happens to have a black hole at its center. So first of all, if the black hole is massive enough, then the sun could basically collapse into it. As the sun would evolve and the nuclear luminosity gets shut off and it starts to get powered by the primordial black hole's accretion, it would actually prematurely turn into a giant star. But it wouldn't get as large as it would have if it went through its normal evolution. So it could turn into a giant earlier than before, which is a bit dangerous for humanity, but it wouldn't grow as big as it would have if it was a normal red giant star. And that's because when it reaches basically its maximum extent, then the black hole is big enough to basically eat the rest of the sun before it can expand any further. Now, that being said, based on the models that we presented in our paper, the future sun still gets hot enough to boil off Earth's oceans. So we still need a plan B, and it could even happen earlier than the normal red giant sun eating the sun. So it doesn't really spare us, unless we have, of course, this other scenario that I talked about where the sun could basically directly collapse into the black hole. But then we have other problems, of course. If you, I like to point people to the Wikipedia article on the sun, because the first sentence always makes me laugh. It says something like, the sun is a nearly perfect sphere of plasma that is responsible for all known life in the universe. And you read that and you think, did the sun write this? And so, yeah, I mean, obviously the sun is our primary power source. And so in any which way, this is kind of bad news for us. We need a plan B to save ourselves, either from the red giant sun, or from the black hole sun, or from the Hawking star sun. None of these are good news for us.
Even just the increasing luminosity sun, which it's doing, it's just increasing and increasing. And before it even gets to that red giant phase, it's going to cook Earth just from the luminosity increase, right?
That's right.
Not good. Now, mass is all important here, and we're talking about primordial black holes, but there really isn't, they don't have to be the giant stellar mass black holes that would suck a star in, or a huge supermassive black hole, the gigantic accretion disk or something like that. They can be very, very small, and there really isn't, is there a lower limit for the mass of a black hole?
Yeah. There certainly is. And this is I say certainly. I should say there uncertainly is, because there's so much we don't know about black holes. And I was saying before about our uncertainties with Hawking evaporation. But indeed, this is exactly the kind of problem that Hawking was thinking about. He was asking, what is the lower limit on the mass of a black hole? And the point is that black holes, unless they can feed, will radiate away their mass. And that means that they're shrinking over time. They're evaporating. And so if the Big Bang made black holes, then the lowest mass of these black holes, they would evaporate by the time that the solar system formed. In our paper, we looked at basically all of the black hole masses that are above that limit. Essentially, what black holes would have been still around in the universe by the time the sun was forming. Okay, I will answer this in units of the solar mass. That's very typical, what we like to do. So the sun then has one solar mass, right? The lowest mass black hole that could have existed at the time when the solar system was formed was 10 to the power negative 20 times the mass of the sun. So 20 orders of magnitude less massive than the sun. Very, very low mass object, much lower mass than even an asteroid. And then we found that in order to change the evolution of the sun in the lifetime of the universe, 13 billion years or so. Well, okay, we could say in the lifetime of the sun, 5 billion years or so. The black hole would have to be of order 10 to the power negative 10 times the mass of the sun. So that gives you 10 orders of magnitude of black holes that could have been born in the Big Bang and then survive to the present day and get captured in stars and do nothing to them. And so our universe is broadly compatible with this population of stars, all of which could have extremely low mass black holes inside of them without changing any of their observable consequences. There's 10 orders of magnitude of black hole masses that could be inside of stars without affecting their evolution.
Now, the strange case of variable stars, and we know you're an expert in this, but the idea that stars vary in brightness and can act rather unusually and pulsate, basically. Now, does this model of thinking about black holes inside of stars change the landscape of understanding variable stars in general? In other words, are there types of variable star that just don't make any sense otherwise?
Thank you for bringing up this topic. Yes, this is actually my favorite topic. So my particular area of expertise is pulsating stars. It's great that this fun topic of black holes gets people interested in what I really like to talk about, which is pulsating stars. So I'll start with a remarkable fact, which is that pretty much all stars are pulsating, including our own sun. What's interesting is the sun's pulsations are so slight that we didn't even discover that it's a pulsating star until the 1960s. So the sun has these really small amplitude oscillations, but it's pulsating in millions of oscillation modes simultaneously, and we can measure them. And from the measurements of the sun's seismic modes, we can map out the internal structure of the sun. So this is the miracle of helioseismology. So just like seismology of the Earth, where we can use earthquakes to map out the internal structure of the Earth. We can use measurements of the sun's seismic frequencies to measure the structure of the sun. And the amazing result that scientists have found as of about the 1990s is that our model of the evolution of the sun basically predicted the structure of the sun, and that structure that we measure from its oscillation modes is in very good agreement. There are some statistical tensions which I could talk about, but overall, at least qualitatively, stellar evolution theory accurately predicts the inner structure of the sun to astonishing accuracy, more than 99% accuracy, which by astrophysical standards is basically, a miracle. So thanks to space missions like Kepler, TESS, Corot, MOST, and some other ones, we now have space photometry of solar-like oscillators out in our galaxy. So basically, nearby bright stars, we can measure their very subtle variations in brightness. And we can start playing the same game that we've played with our sun. So I did my PhD on this topic, trying to make the first measurements of the internal structure of other stars based on their seismic data. So this is the field of asteroseismology. And so if you had a primordial black hole that's inside of a star, it would affect the structure of the star. It would affect how it evolves. And the pulsations that a star exhibits, that's reflecting the structure. It's basically, it's its normal vibration modes. It's sort of like if a singer sings the right frequency, they can make a glass shatter, right? And that frequency depends on the resonant frequency of the glass, right? There's a certain frequency at which you can put energy into that glass by singing at that frequency. And that glass likes to vibrate at that frequency. And so if you put enough energy into it, it'll vibrate hard enough to shatter. Well, it's the same thing with stars. Depending on the structure of the star will vibrate with certain frequencies. So these are actually, a fun fact about this is that these are actually sound waves inside of the star. So stars are basically making music. Stars are musical instruments vibrating with a bunch of different frequencies at the same time, all depending on their size, their density, their internal chemical composition, and so on. So as a star evolves, its pulsation properties change throughout its lifetime. It takes on different frequencies and it puts different amount of energy into different frequencies. Now, I described earlier how the structure of a star would change if its energy source is a black hole at its center. In one of these scenarios, the star puffs up into a red straggler star, and I mentioned that it's a fully convective red straggler star. Now, the interesting thing about convection is that not only does it transport energy very efficiently, it also mixes chemical species very efficiently. So for instance, our own sun, the outermost 30% of the sun is transporting energy by convection. It's also efficiently mixing all the chemicals, all the elements in the outer layers of the sun. So the outside of the sun is fully mixed, but the inside is not, right? So in the inside of the sun, nuclear fusion is converting hydrogen into helium. And so you actually get some differentiated structure in the interior of the sun, where at the deepest layers of the sun, you have more helium. And as you go towards the outer layers of the sun, you have more hydrogen. And then the outer 30% or so of the sun by radius, it's fully mixed, right? You have like a flat composition profile throughout the outermost 30%. Now, in these Hawking stars, these fully convective red straggler stars, so these red giant stars that are to the red of the normal red giant branch, the entire star would be fully mixed. You would not have these layers that are the byproducts of nuclear fusion. They'd have all been mixed away. Even if the star had undergone some long period, even billions of years of nuclear fusion, because of the efficient convection, you would mix the entire star. And so the star would pulsate in a very different way than normal red giants that we have looked at. So one of the major successes of the Kepler mission is that it's measured oscillations in tens of thousands of red giant stars. And red giants have this very amazing set of seismic signals where you basically see different types of oscillation modes. You have the sound waves that I was talking about, right? These are so-called P modes or pressure mode oscillations in the stars. So those are the sound waves. But then you also have another type of oscillation that we've not yet discovered in our own sun, but we can see in other stars. These are G mode or gravity mode oscillations, and these are confined to the innermost regions of stars. In normal red giants, the P mode oscillations, they can couple with the G mode oscillations to form a so-called mixed mode oscillator. And so on the outer layers of the star, you have these sound waves that are dominant contribution to the oscillation. But in the inside, you have these G-mode oscillations, and they're coupling together. And so you see one mixed oscillation mode. And then you actually see, for that particular combination, you see one mode. But inside any given star, you're actually seeing like 50 different oscillation modes at the same time. And so we can very clearly see this kind of data now in red giant stars. For any given red giant that was observed by Kepler, for example, we can see a beautiful spectrum of different oscillation modes. And then the unique prediction that these Hawking stars would have is that because of the intense outflowing luminosity from the black hole at the center, you mix the star completely, and this would completely eliminate the mixed oscillation modes that you would expect to see in red giant stars. And so this is kind of what I would consider to be more or less the smoking gun for this scenario. It's not enough to see the right number of red straggler stars. You would also need to do the astroseismic measurements of these stars and confirm that they have the oscillation pattern that would correspond to a fully convective star, because that's what's predicted by the theory. Now, unfortunately, no one has yet led an astroseismic analysis of red straggler stars. And it's because it's fairly difficult to do this. If you look at a cluster of stars, which is where you normally are able to identify red stragglers, well, you're looking at like 1 million stars at the same time. So it's very difficult to isolate the signals from one star or another. So yeah, leading an astroseismic analysis of a red straggler is just a challenging thing. And so far, there hasn't been necessarily much incentive to do it. But now I'm trying to work on that. So I've applied for federal grant funding to train a PhD student in the science of astroseismology. And if that goes through, then we will start looking at the oscillations in red stragglers to see whether or not they are actually hosting a compact object at their core. And so, yeah, if we find that these stars have pure pressure mode oscillations, that would be compelling evidence for them to host a primordial black hole. And otherwise, then we know that, at least for the particular red stragglers we've looked at, it was another formation channel that created this red straggler, such as through binary interactions. So from my point of view, it's win-win. We might solve dark matter, and if we don't, then we'll make important contributions to stellar physics.
The Kepler spacecraft was one of my favorites because I was a planet hunter, citizen scientist looking for transits of exoplanets.
Amazing.
But that data, you look at those plots, you see the variability of those stars, heartbeat stars, and things, Cepheid variable things, all this variability in the actual star itself, along with flares and all sorts of things, right there in a little graph. And that was amazing. I wish we had about 100 more Kepler spacecraft just staring at various spots in the sky.
Hear, hear.
All right, Doctor, we are out of time. I very much enjoyed it, and I hope you'll come back sometime and we can talk more in depth about variable stars.
Absolutely. I would love to. Thank you so much for having me on. This was a blast.